Notation refers to the symbols that we use to represent statistics or parameters. Remember that statistics describe a sample, whereas parameters describe the population. Many of them look like regular letters, but they are symbols, and they are usually written in italics. Here we see a few rules of summation. Note that the symbol that looks like an E, sigma, refers to the symbol sigma. Sigma tells us to add all values of whatever it is attached to or next to it. C is a common symbol to represent a constant. It represents the number of items that are being manipulated or used in the mathematical equation. We see X sub I, or we can see I subscripted next to the symbol X. We mean that X can represent any value within a sample. If it was X sub 1, we would know to look at the first value only. If it was X sub 2, we would look at the second value. If it was X sub ij, we would know that X represented all values within the sample for all groups, where j represents each group and I represents each value within each group. What would we mean if we wrote X sub I2? Usually variables are represented by an uppercase letter, usually an X or a Y. If I were to ask everyone their height, I might represent the variable of height with an X. But there would be different values for each person represented by X. The first person would have a height of X sub 1, and so on. Note that these rules of summation do involve some algebra. Take some time to remind yourself of some of the basic algebraic functions and rules that guide these equations. When we represent data graphically, our goal is to provide a visual form by which to show the data or the results of analyses of the data. We could show a frequency distribution which allows for grouping and specificity, or we could provide what are called upper limits and lower limits, midpoints, and even histograms. A frequency distribution is the number of times that something happens. If we were to locate the time it took you to swim a lap, we might have a problem if we used the time to the nearest hundredth of a second. It would be a very long table where no two swimmers would be likely to have the same value. Therefore, we could round each value to the nearest second or nearest 5 seconds, whatever makes the most sense. When we do this, we place different values into the same interval so that they can be represented together. The highest value in the interval is called the upper bound or the upper limit, whereas the lowest value is called the real lower limit or the lower bound. Therefore, any value that falls within these limits is classed as being in the interval. At the center of the interval is the midpoint. We usually see most values grouped together, and some other values that occur more randomly stick out. We'll discuss these outliers later on. We can use a histogram to represent a frequency distribution after we have placed values into intervals. We'll see several ways to plot our data depending on the type of data and how to show the most meaningful representation of it. A stem and leaf display is the most basic form of a histogram, though not truly a histogram. The stem is the vertical axis and is formed by the leading digits, also called the most significant digits. In this drawing, they refer to the tens digit 0, 1, 2, 3. The leaves, made up by the trailing digits, are represented horizontally. The shape of the display looks like a sideways histogram. However, some datasets do not lend themselves well to a stem and leaf plot, as they would contain too many leaves. As we look at the plot, we want to be able to tell not only whether a difference is not just due to chance, but we also want to have a sense of just how big or important a difference is. This is called the magnitude. In the figure on the left, we see a bar graph which uses bars to represent the average reaction time. It shows the average response time as a function of whether the participant was correct in his or her choice of same or mirror. The independent variable is accuracy and is represented on the horizontal or x-axis. The dependent variable is reaction time and is represented on the vertical or y-axis. To the right, we see the second graph with time on the x-axis showing the frequency of video game set sessions as a function of age. When the data points are connected by a line, making it a line graph, it better represents the ordinal nature of the independent variable, which is age. In a histogram, the x-axis represents the scores on the dependent variable. In a line graph or bar graph, the independent variable generally goes on the x-axis. The point of representing data graphically, again, is to communicate to an audience. Always use the best way to communicate. Keep things simple. Generally, the worst graphics are those that include irrelevant features that only add to the confusion. When plotting data, remember these guidelines. Supply main title. Always label the axes. Try to start both the x and y axes at 0. Avoid pie charts. Avoid plots of more than 2 dimensions. Avoid non-essential material. As we attempt to understand distributions, we look at 4 histograms. You'll find that normality is a very important concept in statistics. You may have heard of the bell curve, which is based on the idea that there is a normal distribution of data resembling a bell, somewhat similar to the way the first histogram looks in the upper left. When looking at a plot, we first look for symmetry and see that the upper left-hand histogram is unimodal, one high point. In other words, this plot has one peak and goes down on both sides. The graph on the top right has 2 peaks and is thus called bimodal. On the bottom left and right, we see 2 histograms with a peak in each. You'll notice that the data goes to one side or the other. The data goes away from the peak positively or negatively, creating what we call a skew. In determining whether the skew is positive or negative, the tail, T-A-I-L, tells the tail. The tail, as in a lizard's tail, tells us what we should call it. In other words, wherever the trail is leading, positively or negatively, tells us that it's a positive skew or a negative skew. In a positively skewed distribution, we're seeing bias toward the higher values, and vice versa for a negatively skewed distribution. We might find a skew if we were to ask about something that almost everyone likes and agrees upon. If we were to ask people to rate how much they like pizza, almost everyone would rate it very highly, creating a mode that is very positive. Others that like pizza less would be shown in the lower proportions towards the negative tail of the distribution, with outliers or people who like pizza very little being represented at the very far left towards the negative end of the tail or distribution. While I won't go into this in great detail, I will point out that most of us as statisticians or researchers do not do most of our analyses by hand. Rather, we gain expertise with a statistical program or multiple programs, as different programs are useful in different ways. SPSS is a very robust statistical program that has drop-down menus and is very user-friendly. It does use a great amount of PC resources and is somewhat costly. A similar but less popular program is SAS, SAS. It is free for students and somewhat user-friendly. Our project is free but requires a great amount of coding. However, by doing this coding, a researcher becomes more aware of what they are actually doing. They're also developing background code that can be reused over and over. M+ is also code-heavy, but can perform some very unique analyses, such as structural equation modeling. Excel, which most of us have on a computer of our own, does not require much code, but can do many popular but simple analyses. Using the program of your choice with the data that you have, try adding an outlier to see how plotting a graph will change. We'll get to measures of central tendency in the next lecture.